Today's paper is called Discovering Reinforcement Learning Algorithms, and the paper is going to be exactly about that. So how we discover the algorithms that themselves that we use in reinforcement learning. So traditionally speaking, when we're talking about reinforcement learning and the algorithms that have historically been developed, usually these are very defined, like predefined in terms of their structure. The algorithm or the strategy that your agent is going to use as a consequence of training with this algorithm is not predefined, and you don't know that a priori. But the algorithm itself that you're using is very much structured in a particular way and is derived with human intervention, guided by human, let's say, intuition for how learning should be performed. But there are many cases where nature takes another approach as opposed to what we humans tend to do when we analyze problems. So if you think about how, let's say, a circuit in electronics is built, it's very modular. So you would have different stages within the circuit. Like if it's on a PCB, you would have like an amplifier stage maybe, and then some filters and like other stuff. And the reason for that is we're not very good at taking in complexity as humans. So we build things in a modular way, but nature does things differently in general. So we generally have an overlap between concepts. So for example, in the human body, many things serve multiple functions in a different way compared to what you would have in something that a human constructed. And so there are good reasons to believe that you would actually get better performance in a reinforcement learning algorithm by just letting nature take its course and, let's say, derive some sort of meta learning procedure so that you actually let the algorithms improve by themselves without human intervention. So moving towards AGI might require moving away from these traditional RL algorithms for the reason that I just described. And discovering concepts such as value functions, if we're now going to do that in, let's say, an automated way, would require both an understanding of what to predict, but then also how to make use of that for prediction. So a method capable of discovering value functions for itself may also discover other useful concepts, potentially opening up entirely new approaches to reinforcement learning. So this is one thing, and I think this is a big one when it comes to addressing these kinds of topics. Like we're blind to what we don't see, and currently we think we have some sort of approach that's quite good to train an agent, but we know that nature does it better, right? We have proof of that in all the animals that we can see in ourselves and many other things. So potentially by taking the human factor out of this equation altogether, we might be able to end up at a better end goal, let's say. So in the paper, they introduce a meta-learning framework, which is called Learned Policy Gradients or Gradient. So we have an acronym for that, namely LPG. So that's what we're going to use in the paper going forward. And that jointly discovers both what the agent should predict and then also how to use predictions for policy improvement. So the equivalent of this in terms that we might know quite well from previous videos would be like actually discovering the value function or something close to the value function in terms of the function it serves for the system. But keep in mind what we said before, that we might not have a perfect correspondence here. It might not be just one functionality that any particular part of the system would have, since we don't have a human designer. And then also how to make use of those predictions for policy improvement. So that would be something like, how do we leverage the value function to actually get to our policy? And then from data generated by interacting with a distribution of environments. So we take the data, we take pure data or pure interactions with the data that we have. With the environment that we have, and simply analyze that and try to come up with smart algorithms from the data as opposed to something predefined. And we want to achieve generalization not just across tasks, but also across different domains. And this is a weakness, let's say, of the current approaches, because the current approaches are sort of more or less, to some extent anyway, tailored to the application that you're considering. And this is something we want to move away from. So we know that humans are very good at generalizing across tasks. And obviously there are ways of solving these problems, but we're not capable of doing that at this stage. So moving toward that would probably require a framework similar to this, right? Where we move away from actually designing the algorithm in a very direct way and rather construct some meta learning approach. Okay, so basically we want to specify the objective now in our meta learning framework. So what we're interested in, really fundamentally in doing, is we want to find the optimal update rule parameterized by eta. So these are meta learning parameters of our update rule. Oh, sorry about that. From a distribution of environments. So this is the probability of a particular environment, and then initial agent parameters. So P of theta 0. And here we have basically eta star, which is the optimal set of meta parameters. So these are the ones we want to find, and these would be the maximum then of all parameters we could have, where we're according to these distributions, and we want to take the expected value, or we want to maximize the expected value of G, where G is the expected end of lifetime return. So this is pretty similar to what we're used to seeing in any reinforcement learning theory that you would come across. Like, we're trying to maximize the expected value of our end of lifetime return. And we're doing that within the constraints of our environment, and then maximizing over the parameters that we have. So this is what we want to find with the framework. And in the paper, they approach this by a particular kind of architecture. So we can see the LPG architecture down here, and where we want to start having a look at is the figure. So you can see here that we have parameters theta 0 through theta n, and this is then the end of lifetime. So you get some end of lifetime return. And theta are the parameters of the agent, right? So they're very much specifying what the agent does. And here in between, let's say, or when we update this, we do that with an update rule. And this is where LPG comes in. And you can see here that we have an eta here. So that is the meta parameters. And those are the ones that ultimately tell us how the agent parameters get updated, okay? So the second thing we want to have a look at is here. So this is basically showing us some more details on certain evaluation step. So when we move from theta 0 to theta 1, you can see here that we have a policy pi and a prediction vector y, and these are the input parameters of our LPG update rule. So you can see here that the inputs that we take in is a policy, so our current policy here, and then a categorical prediction vector that ranges between 0 and 1, and then is m-dimensional. So these are both the inputs. And what we can say here, policy is what we like, the way we act or how we act in the environment. Y is a categorical prediction vector. And this is not really a value function. So this is where we're moving away from the standard RL concepts of it. This is, normally you would maybe think of this as the value function, but it's more general than that. We would allow it to encode pretty much any information that it finds valuable. And so there is no clear intuition for how to think about this. It tells us something about the environment, and it's a prediction vector, but it doesn't have as clear of a definition as, let's say, a value function, which is the expected value of a particular state. But based on this, the idea is to be able to maybe get the value function. This is supposed to contain that information, but perhaps even more information. Then we feed that into our LSTM. So this is our model. Our architecture for the network is a backward LSTM network. And once we go through that, we get estimates, pi hat and y hat. So these are the outputs of the network, and they are enhanced in some way, or hopefully they will be enhanced. And these will then be fed back, let's say, and this will be an iterative procedure. So that is how you move from theta 0 to theta 1. And taking a look at, how these interact with each other, you can see that this is a backward LSTM. We say that here. So you basically have the output of this flowing back, or feedback from this flowing into the other one. So they're all interlinked here in the network as well. So that's one observation. And if we have a closer look then at the inputs, we have both the policy here and the prediction, and they will be vector valued because for all states you could have a policy, depending on how it's parameterized, but it would not be a scalar value, right? Because we need to encode more information. So those are the network inputs, and those are similarly the network outputs, or the network outputs are of those dimensions as well. We want to look at some of the more mathematical details of how we update these agents now. We're not going to go into full detail, but just to give sort of the update rules that we're following for these algorithms. So if we have a look at the update rule here, we can see that there are really two parts to updating our framework as a whole. The first one is when we move from a particular set of agent parameters, theta 0 to theta 1, or it could be at any arbitrary time step. We have some sort of update rule there, but there is another one as well, which is how we update the actual LPG. So we have a parameterized update rule here, and this one will need to be updated as well. We're going to start with the update of just the agent parameters, so theta n to theta n plus 1. And the update rule for that can be seen here. As I said, we're not going to go into exact details of how this is derived, but what we can see is just the, exactly what the terms in this update procedure correspond to? So pi hat here is the output from the network, and that specifies the, how our action probability should be adjusted. So we have pi theta here, which is our current belief in how the agent should act, and this is sort of the updated version. Similarly, in the expression here, we can see that we have y theta, which is our current set of predictions, so our current prediction vector, and y hat is basically our updated one. And another distinction between these two is that the pi parameter here will directly influence the agent's behavior. So the agent follows pi. This is an on-policy setting. So it follows pi in making its decisions, but it doesn't do that with y. So y has no direct influence on the agent, let's say. It has a direct influence on it. And if we imagine y as being the value function, as I said before, that's not a perfect comparison, but let's say it's the value function for now. What it would correspond to is indirectly updating the policy pi, because that's going to be dependent on, it's going to get updated according to what this y value is. So when we update our pi, it's going to leverage basically what we know from the y function already. So it has an indirect effect on how the agent is going to act, but it's not as direct as the pi. So that's it for the first step. Basically, for the second one, this is the meta learning stage, where we update our LPG framework, and we also have basically a gradient ascent to how we update that, and it is the policy gradient of the objective. So the objective, we looked at this in the beginning, where we basically want to maximize the meta parameters so that we want to pick the meta parameters so that we maximize our expected end of lifetime reward, which is G here. And that would basically correspond to this direction after we perform a policy gradient on that expression. And we do n updates using the same eta from theta 0 to theta n, and then to find meta gradient direction that maximizes the expected return of G on theta n. And we can see this also illustrated in the figure here. So you can see that we take one of these to basically have one, full cycle of updates for our agent, and then we find the best direction in which to update eta, and then we do this for a number of times. So you can see that we have stacked versions here, basically, where we improve the meta learning update rule. Okay, so that's it for the learning stages, and we're going to look at the environments now in which they train these. So for training, they used 3 different kinds of environments. The first one is a tabular grid world sort of environment, and that's what we can see illustrated to the right here. And in this one, basically the objects have fixed locations. So you have objects in the grid world like this that are placed somewhere, and the episodes terminate with a probability term that is associated with the object. So when you pick an object, there's a certain probability that your episode will terminate. It doesn't always happen, but sometimes. And then the object disappears when it's collected and reappears with a probability of respawn for each time step. So it's not deterministic in the sense that, as soon as they disappear, they reappear. If they reappear at the same location, but we don't know exactly when they're going to reappear. So that prevents the agent from basically just picking these positions and going to them as fast as it can. It needs to actually know that something is there for it to pick up. The second one is quite similar. So the setup is very similar to just the tabular grid rules, but this one has some more randomization included in it. So they're called random grid rules, and there the object locations are also randomly determined at the beginning of each episode. So here we can see that we have fixed locations, or we can't see it, but in the tabular one, we have fixed locations for these, and they're sort of always at the same place. For the random grid rules, they're randomly selected at the beginning, so that's a tougher problem for the agent. And they reappear at random locations after being collected as well, so they can sort of move around within an episode even. The last one that we have, or the third setting that it was trained on, is the delayed chain MDPs, is what it's called. Basically, it works like this, where we have an illustration of it here. We have 2 rewards at the end of our life cycle. So one is +1 and one is -1. The outcome here is going to be determined solely based on our first action. So if we go up here, you can see that we're going to get eventually a reward of +1. If we go down, it's going to be -1. However, and then the states in the middle here are just feed-forward states. So we're not ever going to switch tracks, but once we selected the first action, we're going to stick to that one. And the problem here is that the reward is significantly delayed. So it's a way of training on delayed rewards. And for the agent to figure out, okay, this is actually the step that's going to make a difference in terms of what the reward is going to be in the end. In addition, for each of these ones, we have basically 5 variations of them. So that is to introduce some variance in terms of the environments that we actually train on. Moving on now, we want to have a look at the comparisons that we're going to make. So we're going to evaluate some results going forward, right? But in order to make those meaningful, we want to have some agents to compare this to. So it's a bit tricky in this case because we don't have any discrete comparison in the literature that compare such general algorithms. So we have plenty of reinforcement learning algorithms to compare to in general, but a key feature here is how well we generalize across basically environments, right, or domains. That's one of the key points that we mentioned in the beginning. And so we want to have something that we can basically compare this to in a set of domains. And generally, the RL algorithms that are being developed are not agnostic to the domain. And so they would yield quite poor comparisons because they would be very good on one task, but then very poor on other tasks. So they derived, for this reason, they derived some of their own, let's say, algorithms to compare this to. So the first one is LPGV. So that's a variant of LPG that only learns the policy update rule, pi hat, given a value function trained by TD lambda without discovering its own prediction semantics. So what we're saying here is basically that we're cutting away the y function altogether to see how well can we learn without that sort of internal representation. The second one that we're comparing this to is an advantage actor critic algorithm. So that's, let's say, canonical human discovered algorithm baseline. So this is, what you would compare to if you're comparing it to an algorithm that's very well tailored, which we want to get away from, right? So you'd have to train this in, let's say, this will probably generalize worse across domains, right? But we can still compare it maybe to some extent. So looking now at some of the first results, we're looking now at the same environments as we trained on. So we're not really generalizing to new ones here, but we can see how what the performance of these are on the domains that we trained. We can see from the first one here that LPG is the blue one. LPGV, so the one without the value function, or the one without predictions rather, is the red one, and then gray is A to C. So we can see, first of all, that LPG outperforms A to C on most environments. It tends to perform very good or very well, and for most of these, we can see that the blue line is actually at the top for all of it, or well, not for all of them, but for pretty much all of them, we're ending up in the best place using the blue algorithm. So that's a reassuring result. And maybe a more interesting result is that LPGV is worse than LPG, but not clearly better than A to C. And comparing then LPG to LPGV, that's quite an interesting comparison. So we can see that LPG performs significantly better in general than LPGV. And the only difference, or well, the main difference between these two is that we're cutting out the y function. So the prediction semantics are key for the performance. It's what we can draw as a conclusion for this. So it's not just that we have this y vector and it contains no meaningful information, but really the algorithm is boosted, or the performance of the algorithm gets boosted as a consequence of having this in the framework. So even if it's not a one-to-one comparison between a traditional value function, it definitely adds value to this. And that is an interesting observation. So in order to see what this does, basically we have an illustration here of prediction vectors y. So we have a grid world situation like this, where we have both positive goals and negative goals. And this down here is basically the policy and value that you would expect. And here is illustrations of these y vectors that we have. And what we can tell, and what the thing they point out in the paper from this, is that for some of these, we have large values at positive rewarding states. So comparing this to what we see here, we see that the yellow states here tend to coincide for some of them with the positive rewards. And they're also propagated outwards from this. And this looks very much like a value function, like a traditional value function that we have. And it's quite an interesting finding. So it realizes that whatever it aims to represent here, whether it be the value of the state or not, it notices that that value persists, or that this value still pertains as you move away slightly from the point. So that's quite an interesting finding. In order to see now what information is actually contained in the prediction vector that we get in a better way, they made an investigation specifically for that. So what we can see here, or what they did for the investigation, is they generated y vectors. So that is from the actual approach that we're taking in this paper. And then that is done for many grid world instances. And they add a regression model to this that basically analyzes those y values and tries to predict the true values for the different states using various discount factors. So they're all trained with the 0.995 discount factor, but then we have another one as we predict basically what the actual value for that given state is going to be. And as a comparison for this, they used a TD, so a standard temporal difference learning algorithm with a certain lambda for values, or from values at a discount factor of 0.995, so the same one for comparison. So that is basically what we're comparing here. And the value regression from Y is almost as good as TD at the original discount factor. So what we can see here is in these figures is how well it generalizes to the actual action values, or the actual state values in that particular, for any given state that we're in. And what we can see then for the original one, the 0.9951, when we use that, we almost get as good performance using LPG as with the TD lambda. So what we can see there is Y is pretty much rich enough to recover the original concept of a value function. But the really interesting part is when we look at these other ones. So we can see for the other ones, specifically when we diverge quite far away from the original discount factor here, that the performance of the LPG greatly is far better than the performance of the TD lambda. So if we look at the scales here, we can see that the error of LPG is quite the same, or like quite stable across the discount factor that we have here. But for the TD lambda approach, we can see that the error significantly increases as we diverge from the original discount factor. And what we can see here is basically two things. So the scalar value within the TD lambda is too limited to capture values at lower discount factors. So that's what we see with the performance here decreasing as we move away from the original discount factor. And what it also suggests is that the proposed framework can automatically discover rich and useful prediction semantics that can almost recover the value function at various horizons, even though such semantics was not enforced during meta training. So this is really, really interesting, right? What we're seeing here is we have something that generalizes across what a human designer would basically put in place. So we had a standard concept using the formal reinforcement learning algorithms that are currently in place. And we can see that for the original setting, they perform quite well, but there is more information contained in this new representation, and that we didn't have before. So that is really starting to tap into the potential of an approach like this. The next thing we want to look at is convergence of Y. So we saw now that Y might contain some information that's useful, but one thing that traditional algorithms really have going for them is that we have convergence guarantees on these attributes. So for example, if you have a standard value function, there are, so long as you're using a tabular state representation, so not like a neural network, but if you do this in a tabular way, you have a guarantee that you're going to converge to the optimal value function if you train for long enough. It's much harder to give any such guarantees for Y because Y is such a general quantity. So it's not that we have a pure like a good definition even of what we're going to contain within this function. It's some prediction of the environment, but the only thing we require is that using this function, or the only thing we're trying to get to is that using this function, we're going to get some useful predictions about the environment. And that makes it much harder. And currently there is no performance or convergence guarantees for this quantity. So that's a substantial drawback of this new approach. However, and because of that, they wanted to investigate how well they converge in practice. This is a very limited test that they did, I would say, but nevertheless, they looked at two different prediction vectors and from this environment. So these are the initial predictions and they're randomly generated, but then they tend to converge to pretty much the same observation here. And we can see also in the divergence that it greatly increases as training moves up. So for this case, it seems to, handle it in a good way, but this is by no means a guarantee for the convergence. So that is something to keep in mind using this kind of approach. And for the main result, which is really the thing of most interest, is how well does it generalize, because that's what we're trying to achieve with the framework that we're now proposing. So we can see here in this figure basically the number of training environments that we used. And these are all the toy environments. So the ones we talked about in the beginning. What we're evaluating this on now are Atari games. So they are much more complex than the original ones. So we can see here basically an illustration. These are the games that we use for training, the simple grid world and the delayed reward. And then we're using this to play these very complex games. And there's a big delta in terms of the complexity of these. So the ones we're evaluating it on are far more complex than the ones we're training it on. And what we can see in terms of performance is illustrated in this graph. So we can see our LPG algorithm and the performance on the y-axis. The way the performance is measured is basically in the number of games where the agent outperforms a human agent. So we can see in the beginning, before training, we're basically not outperforming a human one. But once we train on all these environments, where we get to is basically 14 games. So for 14 of these games, after training on the toy environments, we outperform a human actor, which is quite impressive. We can see also on the axis here, some of the other algorithms out there and basically where they place in terms of the same performance metric. So we can see that it performs quite well compared to other reinforcement learning algorithms. And it's quite remarkable given that this one is trained in, well, it's designed to be so general, like as general as it is, it still outperforms some of the simpler ones down here. And well, it's quite close to being on par with DQN as well. The most surprising aspect of this is potentially where the training comes from. So the training comes from a very simple environment, and yet it generalizes to quite complex domains. And another thing to note is that specifically for the delayed chain MVPs, we tend to increase performance a lot compared to the one we had before. And this might actually indicate that some training environments are very useful for boosting the performance. And that brings us basically to the conclusion of this paper, which is that generalization performance improves with the number of training environments in general. So that's what we saw here. And for specific training environments, they tend to have a bigger effect on the performance than others. And this is an indication that we may be able to discover general purpose reinforcement learning algorithms using larger sets of environments. And that would be a massive breakthrough. It generalizes well from the toy domains to Atari games, and therefore may be feasible to discover efficient oral algorithms from environment interactions. So if you could find a proper set of training environments that are sort of optimized to train your agent, that might be a great way to build something that generalizes to a large set of environments and that could do many complex tasks without the need for the same level of human interference as we have currently, which would be really a massive benefit for this area of research. So as a main conclusion, if the proposed research direction, that is the moving away from standard traditional reinforcement learning algorithms for something more general like this, if that succeeds, this could shift the research paradigm from manually developing oral algorithms to building a proper set of environments so that the resulting algorithm is efficient. And that would be a massive breakthrough. So that's what they presented in this paper. I'm very interested to see what this research direction could yield in the future. If you are too, please comment what you think might happen and where you see this field going. That's it for now. Thanks a lot for watching, and see you in the next video.